This will be recorded. Okay, good afternoon, everyone. So today we are going to study about moment of a force about a point in 3 dimension. So this uses a slide also, similar like before, that I obtained from my colleague at University Technology Malaysia, UTM, from Professor Rafiq, Muhammad Rafiq Dato Abdul Qadir. So if previously in the previous session, last week, or no, 2 weeks ago, because last week we did not have class on Monday because of the Econit. Okay, we only had class on Wednesday. So the week before last week, we had discussed about moment of a force about a point in 2 dimension, and we have defined moment as m equals to the force times the distance. And today, we are going to extend that definition into 3 dimension. Okay, from 3 dimension, so it means we have to use vectors. Okay, we have to express the forces in 3 dimension as vectors. So usually, then we will use the unit vector at each of the coordinate, in the Cartesian coordinate, or circular coordinate, or elliptical coordinate, or spherical coordinate. But throughout this course, we will be only using the simple Cartesian 3-dimensional coordinate. Okay, so in expressing them, then in expressing moment of a force about point in 3 dimension, then the moment is usually expressed as a cross product of the two vectors that is connected, or we made them to connect into the beginning point. Yeah, for example, as shown in this figure, when you would like to see the moment due to the forces P and Q, yeah, the moment due to the forces. First is before the moment, yeah. So let's say cross product itself. What is the definition of product? Cross product. So we have two vectors here in 3 dimension. Then the cross product P cross Q is equal to the magnitude of P times magnitude of Q multiplied by the sine of the angle between them. And the direction of the vector, so the cross product results is a vector also. The cross product of the vector will be obtained by using right-hand rule. Okay, right-hand rule. So for example, in this case, P cross Q, it means that the direction will go towards the screen. Yeah? While Q cross P, the direction will be towards or coming out of the screen. Yeah, that is why in this case, even though the magnitudes are the same of the two cross product result, however, their directions are not the same. Their directions are opposite each other. And in vector, direction also plays a role. So in summary, P cross Q is not equal to Q cross P. So this is something which we have to take into account and to be careful when we calculate the cross products of any vectors. We have to make sure that the order where we make the cross product is actually according to the problem in hand. We cannot disregard that. So we have to make sure, what is it? Is it P cross Q or Q cross P? Okay. So the definition of a moment about a point, F, when we make a moment in a 3-dimensional space, and we want to calculate the moment about a point in that 3 dimension. So what we need to do is we need to define a position vector. A position vector whose start point is the point where the moment is taken. Okay, and the end point is the point where the force is acting upon. Okay, so again, the start is the point where the moment is taken, this position vector R, and the end point is the point where the force acts. Okay, so when we define a definition of moment about a point, so the R is the beginning point of the vector R, position vector, start from that point, the point in question here. The end of the position vector R will be where the force acts. And you can take either the beginning point of the force or the end point of the force, later as we will see. So R is expressed also in three-dimensional positional vector in terms of the components in the x, y, and z axis. So we have to express them in as a multiplication of the magnitude at the x and y, z axis to the unit vectors of x, y, and z axis, which are the I unit vector, j unit vector, and k unit vector respectively. The force, similarly, we have to express it in terms of the fxi plus fyj plus fzk. Okay? So then we take moment equals to r cross f. So rxi plus ryj plus rzk. Cross product with fxi plus fyj plus fzk. Please remember that if you write down by hand, yes, you have to put also the cap notation here, okay, because it is a unit vector. Yeah, so rx, ry, rz is a scalar that showing or indicating the magnitude of the component of that unit of that position vector in the x, y, and z axis respectively. Similarly, fx, fy, fz is the scalar representing the magnitude of the force, the magnitude of the component of the force in the x, y, and z axis respectively. So then for each of this magnitude, you have to multiply it with the corresponding unit vector so that then they become vector. Okay, so continue further. So then in 3D analysis, the R and F are resolved into X and Y and Z component. So whenever sin theta equals to, sin theta could be equal to 0 or 1, okay? Because the angle between the unit vector can be either 0 degree, that is when when the unit vector is multiplied or cross product with the same unit vector, I cross product I, J cross product J, K cross product K. And from the formula of cross product, we know that the result of the cross product is the magnitude of each of the vector multiplied by sine theta. So since the theta is 0, then sine 0, we know is 0. So I cross I equals to 0, j cross j equals to 0, k to k equals to 0. Yeah. But when a unit vector is multiplied to another type of unit vector, then the theta will be 90 degrees. So then the magnitude will be 1. The problem is now in which direction. So I cross j, if we know I is in the x-axis, j is in the y-axis. So according to the right-hand rule, the I cross j will indicate the direction will be in the k, will be in the z vector, yeah? in the z axis. So for example, this is x, this is y, and this is z. So I is here. Or let me draw a different color. This is I, and this is we have j. So I cross j means that we're using right hand rule. The direction is from I towards j. It means the product is k unit vector, positive k unit vector. Okay. When I cross k, so I cross k, let me draw with different color. So the direction is from x-axis towards the z-axis. Using x right-hand rule, it means then the result will be in the negative y-axis or negative j. Yeah, this one. What about j cross I? J cross I is from the y-axis towards x-axis. So this is here, yeah, j cross I. So using right-hand rule, we know that the direction of the cross product result will be towards negative z-axis. That's why the result is minus k, because unit vector, so the magnitude is 1. J cross k is from y-axis towards z-axis. So the direction will be towards positive x-axis. K cross k will be equals to I. K cross I, on the other hand, will be equal to from z-axis towards x-axis. So the direction is towards y-axis. K cross I equals to j. K cross j, so it means from z-axis, change again the color, from z-axis towards y-axis, using right-hand rule, the direction is towards negative x-axis. Yeah, so this is the negative x-axis or minus I here. Okay, so this is how the cross product result. So when from the previous slide, yeah, we see that M is obtained from Rxi plus Ryj plus Rzk, cross product Fxi plus Fyj plus Fzk, then we just need to group accordingly, yeah, which one multiplied with which one. So which one becomes K? So this will become from the K components comes from I cross J, which is from Rx multiplied by Fy. The J component, the minus J component here comes from I cross K. The I of the R is Rx multiplied by Fz from the F, etc., etc. Then we group again K here with the K here, so into positive and negative. J with the J here, yeah. So Rx minus Rx Fz plus Rz Fx. K we group with the, so this is K, the I with the I, yeah, etc. Okay. Alternatively, we can also use determinant, yeah, like we have learned in analytical algebra, something like this. Yeah, we obtain IJK, so using the cross product, then we use like this, yeah, something like this. Yeah, usually in my case, what I would use is something like this, IJK, okay, which basically this is similar, yeah, or the same. Then we put the first vector into the second row, Rx, Ry, Rz. The second factor in the third row, Fx, Fy, Fz. Okay. So from here, first is I, so equals to I. Let's see, change first. The I component is this part, yeah, this part, then minus this part. Yeah, and I, since it is in the first row, yeah, and the first column, so it equals to I power to first row and first column, yeah. Minus 1 power 1 plus 1, yeah, power yes, power 2 is equals to 1, okay, equal to 1. Then this one becomes Ry Fz minus Rz Fy, okay, from this formula. Then we then plus J multiply by power to the minus 1 the first row, J is in the first row but in the second row, so power to the 1 plus 2, 3, yeah, minus 1 power to 3 is minus 1, yeah, so it equals to negative. So sorry, it's not give the power like that, but instead multiplied, yeah, multiplied by minus 1 power to first row, then but it is in the second column plus 2, okay, and multiply for the J case, the result will be this one and this one, okay, Rx minus Fz, sorry, Rx Fz, yeah, Rx Fz minus Ry ZFX. Okay, so this is not this should be -1 power to 1 plus 1. Okay, then the last terms is the term from the K, the plus K. K is in the first row. This is -1. -1 power to first row plus third row. Then K is like this. So RxFy negative RyFx. So from here, then we obtain equal to I -1 power 1 plus 1 equals to 1, right? So it positive, stays positive. RyFz minus RzFy. Then J multiply to -1 power 1 plus 2. -1 power 3 equals to negative, right? So this becomes minus J. And then become Rxfz minus Rzfx. Then plus minus K, yeah, -1 power to 1 plus 3 is 4. So it becomes positive. Then this equals to Rxfy minus Ryfx. So if you look this result, the result is equal or the same with the one written in the slide. Yeah. So I usually use this kind of notation, yeah, the determinant notation, to calculate the result of the cross product vector. Okay. Example now. This is the example. Determine the force, the moment of a force F, 3000 Newton here from C to D. Yeah. About point A. So the point A is located here, 1.2 meter from the origin point at the z-axis. Okay, so here the coordinate of the A here is x-axis is 0, right? The y-axis is also 0. The z-axis is negative 1.2 meter. Okay, the C to D here is a vector whose coordinate is known. The C coordinate is 0, y-axis is 2 meter. The z-axis is 0, while the D coordinate here, x-axis is minus 0.4 meter. The y-axis is 0. Then the z-axis is 2.2 meter. So you have to first find the vector CD. Yeah, the force at vector CD using the coordinate system, yeah, has been discussed and taught 2 weeks ago. Okay, so then let's see now. The moment, yeah, the moment of about point A will be RAC cross FCD. RAC is the position, as we see the definition of R. Let's see again. The R is the position vector, which starts from the point where the moment is taken and end at the point where the force acts. So here, RAC is taken from the point where the moment is taken, which is about point A, and ends where the force starts, which is D, yeah, where the force acts either to AC. You can also pick RAD. Okay, there are two options. Either you pick RAC, so this position vector, this is RAC, or alternatively you could also choose RAD to calculate the moment about point A caused by the force F here, this force F, FCD. Okay, so we first express FCD in terms of its unit vector lambda CD. So the magnitude is known, yeah, which is how much? just now, 3000 Newton. Okay. So then we calculate the unit factor lambda CD using coordinate method. Dx divided by D multiplied by I plus dy divided by D multiplied by J plus dz divided by D multiplied by K. Each is the unit factor. Yeah. Do not forget to have cap when you write it down by hand manually. Then 3000, the dx comes from the C to D. Yeah, dx is from 0, the coordinate is at 0, right, to minus 0.4, okay? That's why this is minus 0.4. The dy is from 2 meter to 0, so that's why also minus 2. The dz is from 0 towards 2.2, that's why this is positive 2.2. Okay, so the d itself comes from square root of minus 0.4 square plus minus 2 square plus 2.2 square. And here we obtain 3. The result is 3 meter. So based on this, we obtain FCD equals minus 400 Newton I minus 2000 Newton J plus 2200 Newton K. Then F RAC is known. Yeah, RAC is from A to C. From A to C here, how to get it? The coordinate at C minus coordinate at A. The X part is 0 to 0, so there is no I component. The Y part is 2 meter, yeah, minus 0. That's why it is 2 meter J, yeah. And the Z part is from 0 to minus 1.2 meter. Minus, sorry, from A to C, from minus 1.2 meter to 0. That's why the Z direction is 1.2 meter K. Or alternatively, we can choose also RAD, where we obtain minus 0.4 meter I plus 3.4 meter K. If we choose RAC, for example, here, the upper part here, RAC multiplied by FCD, so 2 meter J plus 1.2 meter K, then multiplied by the factor, the force factor. Force factor is here, minus 400 Newton I, minus 2000 Newton J plus 2200 Newton K. Yeah, so we can then use the determinant. For example, this is I, J, K. RAC, first is RAC, we put the I component is null, no component at I, the J component is 2 meter, the K component is 1.2 meter. The FAC, yeah, the FAC is X component minus 400 Newton I, okay. The J component is minus 2000 Newton J, and the K component is 2200 Newton K. So from here, then the I will be equal to this one, which is this one, I, then 2 meter times 2200, yeah, which is 2 meter, the I component, where is it? Yeah, 2 meter multiplied to 2200, 4400 Newton meter minus this times this minus, and this is, there is a minus here, then become positive 1.2 times 2000, which is 2400 Newton meter. Then minus J multiplied by this 0 multiplied by 2000 Newton is 0. Then minus this times this one, minus times minus becomes positive. 400 multiplied to 1.2 equals to 480, yeah, plus 480 Newton meter. Then plus K to here, 0 multiplied by this one is 0, and minus this minus also becomes plus. 400 multiplied by 2 meter equals to 800 Newton meter. So as a result, then our own calculation here, the moment about point A equals to 4,400 plus 2,400 is 6,800. 6,800 Newton meter I. 0 plus 480 Newton meter is 480 Newton meter. So negative, yeah. 480 Newton meter J. Then plus 800 Newton meter K. Okay, so then we obtain the same result as from the slide. Yeah. Basically, it's the same way, only with the result here shown here in the slide here. It uses more of algebraic notation. In this case, I use determinant notation, but they are the same basically. Okay, let's go further. Then this next question is basically from the after determining the force about due to the force 3,000 Newton about point A. The next question states determine the shortest distance between point A and line of action of the force. So here we use the definition of the force, definition of moment in 2 dimensions. Okay, moment equals to F times D. So it means the distance, the shortest distance between that moment, line of action, and that force, and that point A is the moment about point A divided by F. So the moment is a vector, right? From the previous calculation here, the moment is a vector because it has I component, J component, and K component. So then you calculate the magnitude by square root of mx squared plus my squared plus mz squared. And moment about point A equals square root of that, and we obtain 6,863.7 Newton meter. Then the distance equals to this moment divided by the force, 6,863.7 Newton meter divided by 3,000. 3,000 is the force. So we obtain 2.288 meter, the shortest distance between the line of action of that force and the point A. Okay, so if we draw the line of action of that force, basically is this part there. This is the line of action. So the shortest distance will be something which is perpendicular to that line of action, 2.8. Okay. That is calculated using the definition of moment in 2 dimensions, yeah, which is moment equals to F times D. But when you first calculate the moment in 3 dimensions, you have to use cross product. And you have to use cross product, moment equal to R, the position vector, cross the force. And you have to express each of these as vectors, and then you do the cross product using determinant or using the formula for cross product. Clear so far?
I have a question, Pak.
Yes.
For the RAC component, why RAC component has 1.2 mk? Why it's plus? I mean, why it not becomes minus?
Which one? Can you pinpoint? Can you annotate?
RAC, Pak. RAC.
You can annotate using your mouse. Wait one. Is this in the slide or the previous slide or after?
I don't know. Yes, in this slide.
Yeah, can you pinpoint? Using Zoom, you can annotate the screen.
Really?
If Google Meet cannot.
Here? How can I?
Use the annotate. Go to the meeting control and then choose annotate. Because I have allowed the participant also to annotate on shared content. You can write down there in the screen.
I don't know. Where is it? I cannot find it.
Go to the
Meeting
screen,
information.
screen
Yes.
control, and then find the word annotate.
Ada di view options biasanya juga.
View of.
Ada.
Of view. Swap full screen.
Ada di options.
Annotate.
Yeah.
Here. Find it. This one.
Okay. Yes. Why?
Yes. My question is why it's positive, not negative, because the A it's placed below. I mean,
So
in
why
the
is it
back.
positive?
In
Yeah.
the back.
So RAC means a factor, a position factor from A to C. Okay. So writing in different way, RAC equals to ROC minus ROA. Okay, ROC is the position factor from the origin to point C, yeah, which then equals to the coordinate of C itself. Let's see. Oops. Yeah, the coordinate of C is 0, berapa? 0,2 meter, right? 0, right? So ROC is 0 meter I plus 2 meter J, and the K is berapa? The Z is 0, right? The Z is 0. Okay, Z is 0. So plus 0 meter K. So this is ROC, yeah. Then negative the position factor of A, which is from the coordinate of A basically. So let's look here, the coordinate of A. Okay, so let us draw here. Coordinate of A is X is 0, comma, minus 1.2 meter, comma, the Z, sorry, not, the Y is 0 also, the Y is 0, the Z is minus 1.2 meter. Okay, so from here, let's go to the, oops, so here, yeah. So then we already draw here. So this is minus 0 meter I plus 0 meter J minus 1.2 meter K. So equals to 0 minus 0I minus 0I is 0. 2 meter J minus 0 meter J is 2 meter J. 0 meter K minus 1.2 meter K equals to minus multiplied by minus equals to minus multiplied by minus equals to
Plus.
plus 1.2 meter K. This equals to RAC. Okay, is it clear enough?
Yeah, Pak. Thank you, Pak.
Anything else? Similarly, with RAD, yeah, the RAD can be calculated using similar method. So the position factor starts from the point where moment is taken. The endpoint can be either at the beginning of the force factor or at the end of the force factor. If we took the beginning, then it becomes RAC. If we took the endpoint of the force, it becomes RAD. AD. Okay. Okay, let's continue with the other concept. Here is moment of a force about a point. So in 3D, another operation between two vectors is dot product, which also we need to use later. So a dot product result is a scalar. So when we have two vectors having an angle theta between the two vectors, P dot Q, the result equals to P, magnitude of P multiplied to magnitude of Q multiplied with cos theta. Okay. Q dot P equals to P multiplied by Q cos theta. So here we since the cos theta is the same for both, and since the result is a scalar, it means it does not have any direction. So dot product is commutative. P dot Q equals to Q dot P. So no association to the direction. Okay. So in 3D analysis, when we resolve the vectors into X and Y and Z components using I, J, and K unit vector, then the angle between them either 0 degree or 90 degree, right? So cosine 0 degree is 1. Cosine 90 degree is 0. Okay. So the dot product will only have result when the same component are being multiplied into the same component. So I is multiplied to the I, have 1, will have 1 as the result. But I dot product J equals to 0. I dot product to K equals to 0. J dot product to I equal to 0. J dot product K equals 0. K dot product I equals 0. K dot product J also equals 0. So the dot product only will have result when they are of the same component. I dot I equals 1, J dot J equals 1, K dot K equals to 1. So when do we need to use dot product here in the moment of a force about a point discussion? So we use dot product when we want to determine the angle between two vectors. Okay, because there is this theta here, yeah, cosine theta. So when we know the dot product, we know the magnitude of each of the vector, then we can find the angle between the two vectors. Number 2 is when we need to know the moment of a force about an axis. The previous slide discussed about the moment of a force about a point. Well, now we want to know the moment of force about an axis, not a single point, but an axis, a line, or an axis. Then the third use of dot product is when we want to have perpendicular or 90 degree nearest distance between two vectors or between the line of action. Okay, so this is the same as before. Yeah, we see here when using FD, right? Without any vector calculation, just using the definition of moment into dimensions. So then we obtain the shortest distance between the line of action and that force and a particular point by dividing the moment about that point divided by the force. Okay, let's continue. First application for the use of the angle between two vectors. Yeah. So when we express each of the vector in terms of their x, y, and z axis components, then we express p equals to pxi plus pyj, yeah, plus bzk. Similarly, q is expressed as qxi plus qyj plus qzk. Then p dot q will be equal to pq cosine theta, okay, and which equals to equivalent to pxi plus pyj as we have expressed earlier. Yeah, dot qxi, qyj, qzk, and we know that I dot j will be equal to 0, I dot k equals to 0, j dot I equals to 0, z dot k equals to 0, k dot I equals to 0, k dot j also equals to 0. So the result will only come from pxi dot qxi. So px qx, then pyj dot qyj. The result is PYQY, and PZK.QZK. The result is PZQZ. And then you sum all of these three terms. And this equals to the magnitude of P, magnitude of Q, multiplied by the cosine theta. The theta between them, the angle between them. So then, since we know that the magnitude of P can be calculated from the x, y, and z component of that vector by using Pythagoras theorem, similarly with Q, then the angle between them, between the two vectors, can be calculated from the definition of dot product by the dot product result, P dot Q, yeah, which is this one, divided by the magnitude of P multiplied by the magnitude of Q. Okay, so then we can obtain the angle between the two vectors. For example, here, determine the angle between vectors P equals to 6i plus 6j minus 7k and Q equals to minus 6i plus 33j minus 30k. So, very simple. If we want to know the angle between the two vectors, dot product between P and Q, yeah, P dot Q, divided by magnitude of P divided by magnitude of Q. So this dot, the upper part, dot product, so 6 multiplied by minus 6, 6 multiplied by 33, plus 6 multiplied by 33, plus minus 7 multiplied to minus 30. We obtain 372 as the result. Magnitude of P, you can calculate using Pythagoras theorem, 6 square plus 6 square plus minus 7 square, so we obtain 11. Magnitude of Q we obtain from the square of the Pythagoras theorem of Q, yeah, minus 6 square plus 33 square minus 30 square. We obtain 45. So 372 divided by 11 divided by 45, we obtain 0.7515. And this equals to the cosine theta. So to obtain theta, we just use arc cosine of this value, and we obtain theta equals to 41.38 degrees between vector P and Q. Okay, so far understandable? Okay, let's have a break. Let's see how to first pause recording or stop recording for the first hour.